In this video, our goal is to take further steps on the concept of the binomial probability distribution. To get us going, we will look at some of the characteristics of the binomial distribution. In particular, we would like to ask, under what conditions would an experiment that involves computing a probability necessitate the use of the binomial distribution? So let's get started. For example, to answer that question or to help us learn what constitutes a binomial experiment, we'd like to answer these questions. Which of the following is a binomial random variable that arises from a binomial experiment? We plan to select all that apply. So, to begin, we want to recall from the previous module videos that a binomial experiment is one in which a single trial must have only two possible outcomes. There must be a fixed number of independent or identical trials, and the trials, of course, in this experiment must be independent of each other. And lastly, the probability of success from one trial to another must be constant. So, considering the first example here, we're told that based on previous data, an electronics manufacturer knows that 2% of its computer processors are defective. Suppose the manufacturer randomly selects these processors until one is found with a defect. Let D represent the number of processors it takes to find the first one that is defective. Assume that defective processors are independent. What do you think? Is D a binomial random variable? Why or why not? Let's look closely at the thought process here. What does our D, the variable of interest here, represent? It is the number of processors it takes to find the first one that is defective. So, if I pick the first one, if it's not defective, I'm going to continue choosing another one. So in this case, of course, every time I pick a processor, what I have is a trial. And this trial, of course, has two possible outcomes. It is either defective or good. So, as far as the first condition is concerned, this scenario satisfies the first condition. Then, do we have a fixed number of trials in this case? Let's think about that. Well, if we pick the first processor and it's defective, well, we stop. However, if we pick the first processor and it is not defective, if it is good, then we have to continue. Well, who knows where that stops? In other words, we cannot predetermine how many times we have to pick a processor until we find the first one that is defective. It means that this scenario does not meet the second condition. We cannot predetermine the fixed number of processors or trials, as it were, until we get the first one that is defective. That is definitely a concern. So, this first scenario does not fit a binomial experiment, and we cannot define a binomial random variable based on that. Then, we look at the second case. We are to flip a fair coin 5 times. We're going to let T represent the number of times the coin lands showing a head. In this case, let us see if the 4 conditions here are met. To begin, we ask the question, what is a trial in this situation? I would argue that it's a flip of a fair coin the first time, or once. So, does the flip of this coin lead to 2 possible outcomes? Yes, head or tail. So, as far as this scenario is concerned, it satisfies the first condition. Then, do we have a predetermined fixed number of times we're going to flip this coin? The correct answer to that is yes. We're flipping the coin 5 times. So again, second condition, our n is equal to 5 here. What about the third condition? Are the experiments or the flip of the coins independent of each other? Yes. That you flip the coin and you get a head on the first toss has nothing to do with exactly what you get on the second toss. So the outcomes on each of the trials or flip of the coin are independent. So third condition is satisfied. What about the fourth condition here? Whenever I am interested in getting ahead, that is my success event in this scenario, what you find out is that it's 50-50, 0.5. So the probability, P, of success going from one flip to the other or one trial to the other is constant at 0.5. This is all to say that the first four conditions are satisfied. Condition number 5 is inherently tied to condition 4. And so, as it stands, you'll find that this experiment satisfies all the first four conditions and is definitely a binomial experiment for which we can define a binomial random variable. With that done, we now proceed to the next scenario. A certain bus is late to its final daily stop on 20% of days. So, on a typical day, the probability, P, that it will be late is 0.20, 20%. Now, we're going to take a simple random sample of 5 days, 5 randomly drawn days. And we're going to assume that what happens on each of those days is independent. We're going to let V be the number of days out of those 5 days when the bus is late to its final stop. Does this describe a binomial experiment? Let's see if it meets the 4 conditions again. First of all, what is a trial in this scenario? A trial is a single day, and on each of those days, do we have 2 possible outcomes? In this scenario, definitely, the bus is either late to its final stop or not late to its final stop. So that means condition 1 is satisfied. Condition 2, how many days are we trying? Do we have a fixed number of days we are trying? Yes, 5 days. So in this case, our n is 5, and it is fixed. Condition 2 satisfied. Condition 3, the trials are independent of each other. Well, based on the assumption we are given, we are to assume that each day is independent. That is, that the bus is late to its final stop today does not immediately imply that it will be late to its final stop tomorrow. There are no connections between the outcomes on each of the independent days. So we can say, based off that, that condition 3 is satisfied. What about condition 4? What is the probability of success or probability that the bus is late to its final stop on a particular day? This is given earlier as 0.20. So this is constant based on historical evidence from one day to another. And so we can say that condition 4 is also satisfied. The probability based on previous data that the bus will be late from day to day is 0.20. It stands to reason that this scenario is also a binomial experiment. Then we look at the next example. A manager oversees 11 female employees and 9 male employees. So we have 11F/9M. So they need to pick 3 of these employees to go on a business trip. So the manager places all 20 names in a hat and chooses at random. Let X be the number of female employees chosen. Is this a binomial experiment for which we can define a binomial random variable? Let us see. First of all, if we pick the first, what is a trial in this case? It is a pick from the hat. So this is a pick from the hat. Does this pick lead to 2 possible outcomes? Yes, because of course, once a name is picked, it's either the name of a female or a male. So condition 1 is satisfied. What about condition 2? Do we have a fixed number of names that they're going to pick? Based on this part, we're told that they need to pick 3 of these employees. So condition 2 is satisfied. N is equal to 3 here. Then, what about the experiments being independent? That is inherently true, because picking what you pick on the first one does not necessarily dictate what you pick on the second one. But in a sense, you might begin to realize that the probability of picking any person without replacement begins to what? To change. This is what I mean, that this scenario violates condition 4. Let's think about it. If on the first pick you consider the probability of picking a female, that will be 11 chances out of 20, and the probability of picking a male will be 9 out of 20 on the first pick. Well, on the second pick, which is another trial, if you picked a female on the first pick, well, you're not going to replace that name back. So the probability of picking a female now goes down to, out of 19 people that are left, you're having what? To pick what? You have 10 chances of picking a female out of 19. So in this case, we find that as you go from the first trial to the second trial, the probability of picking a female is no longer constant. So in this sense, it suffices to say that this scenario is not a binomial experiment, because the probability of picking a female from one pick to another is not constant at 11 over 20. Then we look at the last one here. Mrs. Glover writes names of her 30 students on individual pieces of paper and randomly selects the names of 5 students from a hat. Let M be the mean number of letters in the first names of the students. Is this a binomial experiment? First of all, we ask, what is a trial here? A trial here is picking or selecting a name randomly from the names of the 5 students in the hat. So, as it stands, we reason that in every trial here, are we going to get 2 possible outcomes? What you might reason here is that even the first condition might not be satisfied by this scenario. In other words, this scenario is definitely not a binomial experiment, because there's no guarantee that when you pick the first name, you're going to get 2 possible outcomes that are well defined. As it stands, the last scenario here is not a binomial experiment.